Hello. Gonna wait for a few more people to join. I'm gonna have them for lunch. So, yeah, my parents are visiting, so my refrigerator is like really full because I've been making stuff, my mom's been making stuff, we've been going out. So there's um, a lot of food in my refrigerator that I have to get through. So I will try to communicate something to you in Spanish because I'm trying to learn Spanish. So I'll tell you a story from my IB physics class. Okay. Yo pregunto mis estudiantes cómo se dice flor en español. Y ellos me dicen flor es caca. ¿Es verdad? Sí. Sí, yo hago los tareas de español. I sound French. Oh, thank you very much. Ellos me comprenden. Oh, someone disliked my stream. Okay. I think my French accent is definitely better than my Spanish accent, but I'm working on it. Okay. So then, uh, yo digo, right? It's yo digo, I think. Yo digo, um, yo digo, hoy yo hago una grande caca. And then they all laughed at me. Okay, so I'm going to start teaching physics now. Because it's hacer caca. That's how you say it, right? So anyways. Okay. I'm having too much fun today. So let's start talking about physics, which is even more fun. Oh my gosh. All right. So Here we go. Today we are going to be talking about the drag force. Okay. So the drag force is the force of air resistance. Okay. And we're going to call the drag force F sub D. And so there are lots of, the drag force is really complicated. So we are going to, we're going to learn a simpler version of the drag force, okay? So this is the form of the drag force that is used on the AP exam, okay? It's called Stokes drag, okay? And this formula for the drag force is minus K times the velocity, okay? So a couple of things to note. One thing to note is there's a minus sign because the drag force is an oppositional force. Okay, if you go to the left, then drag force points to the right. If you go up, drag force points down. So it's an oppositional force. It is proportional to the velocity. So that means that the faster you go, the larger the drag force. Okay. So these two properties that you see right here are, no matter your model for the drag force, no matter the model for the drag force, they are all going to have the property that they're oppositional and that they increase with speed. Okay. This constant K, it depends on two things. The first thing it depends on is the shape of the object. So if something is really aerodynamic or really hydrodynamic, then it's going to have a smaller K constant. It has less drag acting on it. And then the other thing it depends on is the fluid that the object is moving through. So I'm considering air as a fluid, water as a fluid, any gas as a fluid. So if the thicker the fluid is, the larger the K constant is going to be. All right. So for example, if you are going through air, the K constant is going to be relatively small, whereas if you go through water, the K constant is going to be large. If you go through molasses or honey, the K constant is going to be even larger still. All right. So this is the model for the drag force that we're going to use in this class. But I have to tell you that this model is only appropriate if you have something that is really small. And when I say small, I mean really small, like the size of a bacteria. So bacteria experience Stokes drag. Or low speeds. So this model of drag is appropriate to low speeds and or very small objects, okay? Which is not very useful, but it is the model that we use in the AP exam because it is the simplest mathematically. So a more realistic model is going to be one where the drag force is minus K V squared. So again, this model increases with speed, just like the other models. All models of the drag force increase with speed, but this one increases faster. It increases quadratically, and it has a minus sign out front because it's oppositional. So this one is used for like airplanes and humans and yeah, things that are larger and going fast. But we're not going to talk about that. Okay. All right. So, let's go ahead and what we want to do is we want to, I'm going to consider our first scenario. So let's say scenario 1. Motion through a fluid without gravity. So you're moving through a fluid without gravity. So an example of this would be, what if you had a spaceship, it's cruising through a nebula. Now, as the spaceship cruises through the nebula, the spaceship is bumping into the molecules within the nebula, and those molecules are going to slow it down. Okay? There's no gravity because it's in outer space. So eventually what will happen is the spaceship will come to a stop. All right? And we want an equation for the velocity as a function of time. Okay? So we want to know, what is the velocity as a function of time. So to do that, we are going to write Newton's second law. Net force equals ma. And because it's motion through a fluid without gravity, the only force present is the drag force. Okay? So minus kV is the net force. And then I'm going to write the acceleration as dv dt. Now we're trying to solve for the velocity as a function of time. And this is an example of what is called a differential equation. Okay? As opposed to an algebraic equation. So an algebraic equation is the one that you are most used to. It's one where you solve for x, for example. X is a variable. Okay? And you usually solve it by, I don't know, doing systems of equations or moving the variable to one side and moving everything else to the other side, stuff like that. A differential equation, we're not solving for a variable, we're solving for a function, and that function is the velocity as a function of time. This equation is going to have the function we want, v, and it's going to have derivatives of v. So that's why it's called a differential equation, because it has the function and the derivative of the function, and maybe the second derivative of the function, the third derivative, etc. Okay? So this is a trickier equation to solve because it has, it has the derivative. So in order to solve this equation, I'm going to have to use calculus. So if you are concurrently enrolled in calculus, and you haven't gotten to how to solve this yet, that's okay. I'm not going to ask you to solve the differential equation on a test, okay? If you're not even in calculus, that's okay, because all you're going to use is the result in the interpretation of the solution. All right, so don't panic, but you're not going to understand about the next 5 minutes. Okay? So how do we solve a differential equation like this? Well, what we want to do is we want to do what's called separating the variables. Okay? So when we separate the variables, see how this is velocity as a function of time is what we're looking for. So we're going to put velocity on one side of the equation and time on the other. Okay? So to do that, I'm going to divide both sides by k. All right? So that gives me Actually, I'm going to divide both sides by minus. What am I doing? Take it all back. I'm goofing. I'm going to multiply both sides by dt. Okay. Now notice how I have dt over dt. So the dt's cancel out here. They don't cancel out over there. So in the next line, I have minus kv dt equals m dv. Now I'm going to divide both sides by m. Okay, so those cancel out, and on the left-hand side I have minus k over m v dt equals dv. And then I'm going to divide both sides by v, and these v's cancel out, and I get an equation minus k over m dt equals dv over v. All right, so this is a separated equation because I have everything with velocity in it. So dv and v are on the right-hand side. Everything with t, dt, is on the left-hand side, okay? And the constants, which are k and m, it doesn't matter which side you put them on, okay? They can be on either side. So this is a separated equation. So once you separate the variables, you then integrate. You are going to integrate both sides of this equation. K and m are constants, so I can pull them out of the integral. I'm going to integrate them from 0 to t. Okay, and at time 0, the velocity is at some initial value, v naught, and at time t, it's at some final value. Okay. So this is just as simple as an integral of dx. So the integral of dx is just x, right? So on the left-hand side, I have minus k over m times t. And the integral of dx over x, as you might recall, is natural log of x. Okay? So on the right-hand side, I have natural log of v, and I'm going to do the limits. Natural log of v minus natural log of v naught. Okay. You might recall from your math class that natural log of a minus natural log of b is natural log of a over b. Okay, so I'm going to write that as natural log of v over v naught is minus k over m times t. All right. And so now I'm going to do e to both sides. So the e cancels out the natural log, and on the right-hand side, I'm going to have that. On the left-hand side, I'm going to have e to the minus kt over m. And then I multiply both sides by v naught. And what I get is the velocity as a function of time equals v naught times e to the minus kt over m. All right? So this is the equation. So if you don't know any calculus, this is the equation you write down. Okay? And that's completely fine. So what I want you to realize is that there is an exponential decay of the velocity. There is an exponential decay to 0. So if we were to graph the velocity of the spaceship as a function of time as it goes through the cloud, we get something that looks like this. Okay? Starts out at v naught and it exponentially decays. What if the spaceship is more massive? The more massive the spaceship is, the more inertia it has, so the more ability it would have to plow through the nebula. So it's going to slow down at a lower rate. So the more massive it is, it might decay to zero like this. What if the K constant were really large? What would a really large K constant be? It would mean something that is not very aerodynamic, traveling through a thick nebula. And in that case, the velocity is going to decrease to zero very rapidly. Okay, so it might do something like this. So you should know what this graph looks like, and you should know that it is described as an exponential decay of the speed. We have an exponential decay of the speed to zero. How quickly it decays depends on the mass of the spaceship and the fluid that it is traveling through and how aerodynamic the ship is. Okay? So that's scenario one. Scenario two is a little bit trickier. Scenario two is motion through a planet's atmosphere. So now we're going to have gravity, okay? For this problem, we are going to consider the situation where V initial equals 0, so it starts at rest. So this might be like a skydiver jumping out of a hot air balloon or something like that. And we are going to take downward to be positive. Okay, so this is one of the only times in the class that downward will be positive. So what are the two forces that are acting on the object? It could be a skydiver, it could be something like that. You've got the weight force, mg, going down. And you've got the drag force, F sub d, going back up. All right? So if we write Newton's second law, net force equals ma, yeah, gravity and friction. Generally speaking, if it's friction from an atmosphere, we call it drag. But drag is a form of friction. Okay. So our net force is going to be the downward forces minus the upward forces. Okay. So we have mg minus kv. All right. Remember, downward is positive for this problem. This is one of the only situations in our class where we would take downward to be positive. And then that equals m times dv dt. So this is the differential equation. You should be able to write this down and understand what each term means, even if you are early in your calculus understanding. Okay? This is just a restatement of Newton's second law. I've seen many times on the AP exam, they ask you, write down the differential equation. And what they mean is you should have an equation with derivatives plugged in where you can, and usually it's a restatement of Newton's second law. Okay? So one of the interesting things about motion through a planet's atmosphere is as the object falls, it's going to pick up speed. And as it picks up speed, the drag force increases. Okay? So as time goes on, you have the drag force is getting bigger and bigger and bigger because you're picking up speed, okay? All right? And eventually the drag force will become so large that it matches the weight force. And when that happens, you have something called terminal velocity. So because the Earth has an atmosphere, you do not accelerate indefinitely. So the faster you go, the more you have drag force pushing back against you, the more you have air resistance pushing back against you, and eventually you'll reach a maximum falling speed, okay? All right? So there's a limit to how fast you fall. So we can actually calculate that, because once you reach your terminal velocity, you have an acceleration of 0. Okay? So what if we set the acceleration equal to 0? Then we have mg minus kv equals 0. Okay? And so this equation no longer has the derivative of the velocity in it, and so therefore it's an algebraic equation that we can just solve. We have the velocity equals mg over k. All right? So that's the terminal velocity. I'll denote it by v sub capital T for terminal velocity, and its value is mg over k. All right? So you should know how to derive the terminal velocity in this case. So how you get the terminal velocity is you set the acceleration equal to 0, and then you solve for the velocity. This equation makes perfect sense, okay? What if the mass of the object is bigger? The more mass the object has, the more inertia it has, okay? And the more inertia it has, the easier it's going to be for that or the more difficult it is going to be for drag force to stop the fall or to slow the object down. So the bigger the mass is, the higher the terminal velocity. The more gravity you have, that means that the weight force is bigger, so you are able to build up more speed before the drag force can halt your acceleration. Okay? So G is in the numerator. The thicker the atmosphere is, the slower you're going to be able to fall, right? If you're falling through molasses or you're falling through water or something, you're not going to be able to fall as quickly as if you were to fall through the air. So the bigger the K value is, the lower your terminal velocity. So this equation makes a lot of intuitive sense. So that's nice. What else did I want to say? Your terminal velocity. So this gets really complicated. The more accurate we want to be, the more complicated it gets, right? If we think about it, if you're falling, you're getting closer to the surface of the Earth, right? You're getting closer to the surface of the Earth. So gravity is actually getting stronger as you're falling. So G actually depends on your altitude. Very slightly, but it does. And also, the thickness of the atmosphere depends on altitude, right? Because the higher up in the atmosphere you are, the thinner the atmosphere is. So your terminal velocity actually depends on where you are within the atmosphere. This is kind of interesting. There, a couple years ago, a guy named I think Felix Baumgardner or something like that. Felix Baumgardner or something. went up in a hot air balloon to like a really, really, really high altitude. Like, so he was so high up you could see the curvature of the Earth, and he jumped from the hot air balloon, and he reached a terminal velocity that was really huge because he jumped from such a high altitude that there was very little K constant. So he picked up a huge amount of speed. And then once he got lower into the atmosphere, the K constant went up, and he actually slowed down. So while he was falling, he was slowing down because he was entering a thicker atmosphere. It was kind of cool. Okay? So anyways, now we want to solve this differential equation. So what I'm going to do is I'm going to take both sides and I'm going to divide by k. All right? So if I divide both sides of this equation by k, I have mg over k minus v equals m over k dv dt. All right? So that's going to allow me to write mg over k as v sub t. So I have v sub t minus v equals m over k dv dt. All right. So now what I'm going to do is I'm going to multiply, actually I'm going to divide both sides by v sub t minus v. That gives me 1 on the left-hand side. All right. Then I'm going to multiply both sides by k dt over m. Actually times minus k dt over m. And so that's going to give me minus k dt over m on the left-hand side. It's going to give me k. The k's cancel out here. The m's cancel out. The dt's cancel out. The only thing that doesn't cancel out is the minus sign. So that minus sign is going to flip the order of these two. So I have dv over v minus v sub t. So this is a separated equation because we have all the velocities terms on one side, we have all the t terms on the other side. So now we integrate. Once we separated, we integrate both sides from 0 to t, and the velocity, because it starts at rest, the initial velocity is 0, and the final velocity is v. So doing this, the right-hand side, we get natural log of v minus vt, and that's evaluated at v and 0. And then on the left-hand side, we have minus kt over m. Okay, so now I have to do this subtraction for the evaluating the integral. So I have minus kt over m equals natural log of 1 minus v over vt. And I'm skipping some algebraic steps there. I hope you can, I apologize. To get rid of the natural log, I do e to both sides. So I have e to the minus kt over m equals 1 minus v over vt. Okay. And then I can solve this for the velocity as a function of time. It's vt times the quantity 1 minus e to the minus kt over m. So this is the equation you write down if you don't know calculus. Okay? That's the final answer. So what if we were to graph this? Okay? If we were to graph the velocity as a function of time, the velocity starts at 0 because that was just the way that we designed the problem. Okay? So it's something that was jumped out of an airplane that was, or jumped out of a hot air balloon, something that started at rest. Okay. And then it's going to approach the terminal velocity. So that's going to be a horizontal asymptote for this problem. All right. And it's going to exponentially approach that. So it's going to asymptotically approach the terminal velocity. All right. So there you have it. We asymptotically approach the terminal velocity. And these conclusions are true no matter the model of the drag force. It's just the specific form of the function is a little bit different depending on your model of drag. So if you needed a super duper accurate velocity time graph, then you would need to use a more complicated model. But this model is going to be qualitatively correct. So, no matter the model of drag, you're going to asymptotically approach a terminal velocity, okay? No matter the model of drag, if you are coasting through a nebula, your velocity is going to asymptotically approach 0. It's just a question of, is it exponential decay or is it something that is almost exponential decay but is described by a different function, okay? So anyways, okay, so yeah, so there's a really good question. Does that mean you can never actually reach terminal velocity? In this model, the answer is no, you can never reach terminal velocity. But you have to remember that this is just a model, okay? Actually, what would happen is, because your velocity isn't really changing continuously, what happens is every time you're hit by an atom, boing, 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 your velocity changes abruptly, but by a really tiny amount. So actually, even if something is standing still in the atmosphere, it's being hit by atoms randomly, okay? So even something that is at rest in an atmosphere is actually moving around ever so slightly due to the impacts of the individual atoms. Now, because there are so many atoms that are so light and the impacts are happening so often, we don't actually see this. But you can do an experiment where, and this is the experiment that was done, they took a grain of pollen and they set the grain of pollen into a glass of water and they looked at the grain of pollen under the microscope. And what they found is that the pollen grain does not stay still. It's actually jiggling around in place, okay? And that type of motion is called Brownian motion. And Brownian motion was one of the first pieces of evidence of, well, it's a direct piece of evidence for the atomic model, right? Because we knew that there were atoms for sure, 100%, once we saw Brownian motion, because the only way you can explain these fast jitters is via impacts of individual atoms hitting the pollen grain and pushing it around. So yeah, that's kind of cool. It's called Brownian motion. Actually, Einstein won the Nobel Prize for, in part, for Brownian motion. All right, he was a contributor to that. Okay, so that's my class. I will see you in the Zoom room.